It's a great pleasure to be here. It was really an enormous pleasure to receive a referee comment from the workshop. They were both very enthusiastic and very, very, very critics. I had 18 pages to swallow for the final version. That was a great pleasure. I would dream two things. I would dream first to come back in 10 or 20 years from now to make some functional Perl explaining that we can do a great deal of programming with inverse semigroup, which are slight variation on these semi-rings. And also I would like to come back, possibly also in 20 years from now, with some wonderful thing like the Riorso opera and showing that, well, this can be used. But in the meantime, I will just talk about theory, because I lack of engineer, and the theory is still under development. Also, another ambition is, I would like not to do computer science for music, but rather the other way around, music for computer science, and trying to discover it in that very old language that is more or less formalized, what concept, tools, idiomas, or metaphors can be used in computer science. And the T-calculus I will talk here is an example of that somehow. That was 2 years ago I decided to do a music modeling, and that was the start, and it eventually led to what I will present today. Okay, everybody is hearing me correctly, and that's all fine? Okay. So the very first example was really that Parker tune, so my little blue sweat shoes. So let's hear it again, because it's Parker the Great. So you have the score, you can follow. And if you're not a musician, then we'll just hear it a second time, just to be sure we understand what's happening. Okay, and so the goal is to model that simple piece of music. And it's very clear, reading it or even listening to it, that what's happening? 3 times something, then something a little different. And that's musicology, and that's musical analysis. And if I want to model it, the simplest thing we can think about is to model music sequences like strings. So I put these notes in sequences. I only remember the length of every note. So this is the sequences on the bottom of the page. This is for the first part. And then this is for the second part. And then these strings can be combined. Because we are computer scientists, we know what strings are, and we combine them. So we combine them in sequence. Okay, we need to add some pieces of rests. And the resulting is that, so you can just have a look at the last line. For some reason I was making trees. And what immediately shows up is that we have to insert rests of various size, first 5, then only 1, then only 8, then 8 if we want to repeat the sequence. And well, we have lost somehow this very simple musical structure I described, 3 times something plus something else. And what is just clear is that there is just no musician that will think of the rhythm of that jazz melody. We're counting this number of rests. Whenever you start real counting with musicians, they are totally lost. And if you hear the way Charlie Parker is playing the theme, he's actually improvising a little already. So these strings are not exactly what the strings are written, but some variation on it. So how can you do the modeling of that music? And the solution is actually to somehow distinguish the sequence of notes themselves that are true music with the way they are used. And this is very well known in music, actually. This is the notion of anacrusis. What is an anacrusis? An anacrusis is something that starts before the downbeat, the first beat of the... So the real first pattern is actually da-da-ba-da-ba-da-ba. And so at the beginning of this pink or violet or whatever color, This is the real start of or the logical start of that music sequence. And this is even modeled in music by the first bar. So the first pattern can be modeled like this, and for some technical or to be more comfortable, I even add in the pattern these eight rests that comes after. And I could do that with the second pattern, with an anacrusis that is a little longer. You can even learn a little French, because it's anacruse in French. And then to combine them, how do I do? Well, I just put them one after the other. But after, with the fact that this anacrusis will overlap the preceding sequences. And doing that, we really have our original structure, which is 3 times something plus something else. And this is tiled strings, or tiled streams modeling. And behind this, there is very, very rich mathematical theory, inverse semigroup theory. And the T-calculus is an attempt to promote the use of inverse semigroup theory towards programming, and I am trying to promote it towards system modeling. I will go to a congress in Rennes in 1 month, and I'm trying to promote it. Well, I'm trying to promote it in every direction, and we'll see what will pop up. I have no idea when I started. Can you tell me how many? Quarter of an hour would. Okay, cool. Okay, so what are tiled streams? How can we abstract a little from what do exist in music? Using music for computer science for sure will mean abstracting these ideas or concepts that may appear in music. We will need to do something stronger. Somehow, as plane, somehow plane are flying almost like birds, but they don't need to shake wings, and that's better. Although they do shake wings, actually, I was a little scared on my way to here. Okay, so what is a tiled stream? The idea is that we first have a B-infinite sequence, so mapping from the integers, positive or negative, into some basic type, A. And I had on that a synchronization length. And actually, the synchronization length do specify 2 points. 0, which is the default beginning of that will be called the synchronization window, and 0 plus that synchronization length, that in the example is 8, that will be the end of the synchronization length. Okay? And this is a tiled stream. And the idea is that this first, but this just, in music, this just model 1 start bar and 1 end bar. And the distance between the 2 bars can be arbitrary, of course. So it might be the case, even, and I will come on that later, that on the side there are zeros, and actually this means that we distinguish between some synchronization length or logical duration, which will be used for synchronization, and some realization length or true duration, which will be where exactly the real notes are. Okay? And then there is notion of product that is associated to that, is the following. I take 2 tiled streams, and the product is decomposed really into 2 steps. First, synchronization. I put the last bar, or the exit bar of the first tiled stream right at the same time the start bar of the second stream. And then, so this is synchronization. And then I perform a fusion, and here, in the simplest case, the fusion just mean putting the 2 signals one aside the other. So if I start from a first signal with basic type A and the second signal with basic type B, then the resulting tiled signal of their synchronized product will be of basic type A times B. And the resulting synchronization window, I keep the entry point of the first signal and the exit point of the second signal, okay? That one is reserved, and that one is reserved. And the synchronization point in between is lost. Okay, so that's the basic principle. And this is somewhat a free case, because my fusion is sort of quite limited. So the resulting synchronization length of the synchronization of the two tiled signal is the sum of the duration length. Okay? But I can do... Yeah, please.
I would like to stop you now so I can make sure I understand
Yeah.
what you're saying before we go on.
Yeah, please, you're welcome.
So is this, there's an overlap here. Your T1 has a synchronization length of 8.
Yeah.
And your T2 has a synchronization
Length of 4. Yeah.
The
So the resulting...
has a synchronization length of 12.
Yeah.
And so what is the A value at, say,
Okay.
9?
So if I understand correctly your question, you are asking, when I mark 8 here on T2, what real value is?
What's the value for T1 in the little gray box above or
Yeah.
diagram?
So I at first synchronize the two signals and then I glue them. So what was the value of T2 at 0 here? Is there.
Yes.
Okay. And what was the value of T1 here at 0? It's there.
And what is the value of T1 at 8 or 9?
So here it will be, in the synchronized product, here it will be T1 at 8 and T2 at 0. Sorry, and I said here it will be T2 at 4 and here it will be 0. So this is explained in that equation. Yes? Yeah, yeah. Yeah, of course. Yeah, yeah. Yeah. So the synchronization length do matter because it tells when I take two tiled signals, they will be positioned one with the other. And the synchronization length of T1 says by how much I will translate T2 before synchronizing it with T1. Okay?
There's no constraint that say T1 at T has any relation to T1 at T plus A.
No. For the moment, there's just no problem. And this is the free case. The parametric case is that instead of just making this sort of Cartesian product of the output, I can apply an arbitrary function. So, for instance, an operator. And here I assume that I have an operator that took two signals of type two basic type A times B and produce some C value. Then I will define the tiled or the lifting of the operator to tiled signal as follow. T1 up T2 will be just the same. First I position the two tiled signal one with respect to the other, and then I do here make some more general fusion. I do compute vertically the result of all value of T1 and corresponding value of T2 applying the up operator. Okay, and again the resulting synchronization length of the operator applied to two signal is that. This is even a drawing to describe this. Okay, so V1, V2 somewhere there, and V3 that just equal V1 up V2. Okay, an example. I assume that I have a function map that takes a function from A to B and an argument from A and produce an element from B. Then I can have a tiled signal of function value, a tiled signal of argument, and I can apply with such an operation all values of the F streams on all values of the T streams. And here there is something a little new, is that the synchronization length of F is just 0. So the beginning of the tiled signal F and the beginning and the end of the synchronization window is just the same. So when I compute map F of T, then the resulting synchronization window is just that of T. And this can be very convenient if we want to preserve this the space the signal will take into some music composition. So this leads actually to realize that there are two important sort of meta operator that can be applied on tiled signal, the reset and the co-reset. The reset R of t amounts to put the end of the synchronization window straight at the beginning. So to merge to move the end to the beginning, and the co-reset L of t amounts to move the beginning to the end of the synchronization window. Okay? And these are two. So this allows actually to define some sort of parallel composition. Here, if I take two signals T1 and T2, I can define sort of a fork of T1, T2, means starting T1 and T2 at the same, synchronizing them at the beginning of their synchronization window, and this can be done that way. And I can also make sort of a join, which means I synchronize on the end of the synchronization window, and this can be done that way. And I will try to move a little faster because I want to talk a little. I have a lot to say. Okay, all this notion of tiled strings relate with what the typical data structure that can be used in music, and so there is some link with. Referees pointed out that Paul Hudak has worked on this polymorphic temporal media. And also, there is also in language theory a notion of omega semigroups that try to merge strings and streams. So the first remark is that we can embed the classical notion of finite strings into these tiled streams. How do we do? We assume that in our alphabet we have some zero value that will be neutral for some addition, and the embedding of any finite string will be the tiled signal. So the finite string will be here, and the synchronization window will be just aside the finite string. And before I put 0 later, I put 0. And if I do that, then I just see that not only I can encode any strings, but also the product of my tiled streams do encode the product of finite strings. Okay, I need to make the sum then, so that the type of my result is indeed what I expect. I can also embed streams. How do I embed streams in the sense of infinite strings? How do I do that? An infinite strings will be a tiled stream where the synchronization window is of 0 length. And then I have my infinite sequence of value. And the important operators on to start two streams at the same time, and this can be just modeled by the same product of tiled streams, okay? And there is even a mixed product that you take an infinite stream and you put in front of it a finite string, and you obtain an infinite stream, and this also can be encoded in this algebra of tiled streams. I won't. Okay, so the T-calculus, just take some syntax for that. A constant will be a tiled stream of the synchronization duration 1. The value in that synchronization window will be the value of that constant, and everywhere else 0. 0 because it's cool. 0, it don't make noise. And then we have variables. We can apply function. That will be the type of the semantic will be the type of semantic I have described. Declaration or sort of fixed point in order to allow a fixed point definition. And this reset and co-reset. And so, for instance, an example, I have a function that take a vector of length n of type A and produce a single element of type A. This can be understood as an effect, an audio effect. So it looks at the windows of length n, and from the values on that windows produce a single échantillon, whatever it is, sample. Thank you, Jean. Applying this audio effect to a given tiled stream can be simulated that way. So the idea is that I take plenty of copy of the tiled stream and I move them forward, and And well, there is some syntax to express this. I won't defend the beauty of the syntax so far, sure. So the semantic, what can it be? At the moment it's rather ad hoc. So you have variables, you need some environment that says what are the value of the signal. You put everything to 0, no noise, and then you iterate. And you pray God for your iteration to converge to a single value. And that's the semantic of the calculus program. Okay, it's not that effective, you're right. Here are the rules for the semantic. They are on the paper. I won't comment. Some types. First, type inference system that allows you to compute what is the basic type, what are the basic types of the tiles streams, and what are their duration length. All that is static. There are rules that do tells you what is that. Another typing rule, I said it might be the case that my tile signals above some limits are just 0. So what is really important is between what date and what date they are relevant. So this is a notion of synchronization profile. So aside the window, there might be some distance where you do have to take into account the values of the signal, and this is a synchronization profile. The point is that if you make the product of two tile signal, and you ask what is the resulting synchronization profile, well, actually you are reinventing the free inverse monoid of one generator, connected with free inverse semigroup theory. I won't comment on that. Or not more. There is a type system that infer all that. Okay, that's cool. And okay, how do you execute a T-calculus program? Oh, that can be a little difficult because I can move signal backward, forward, synchronize them in quite a fancy way. A priori, a T-calculus program probably have no semantics. And if it has a semantic, it's something a little weird. You have to take some value at the minus infinity, plus infinity, or whatever, and combine them, and you're totally lost. So actually, in the paper, and I will be a little fast on it, the question is that when you have, here you have a simple program, it's already very simple, but already very complex. You have to breathe deep and to look at it for some time to understand what it is doing. But the question is, OX depend on itself in that program. And if it depends on itself in a nice way, then it is computable. Okay? And it occurs that, well, this is a little explained in the drawing, but here is the important line. So here is the important line, and it says that, well, the value of the program essentially depends on the value of X one step before. Okay, so it means it is computable, provided at the beginning it is 0, then you can, it has some causal property, as someone was describing 2 days ago. And probably there are many links with what I heard 2 days ago and what I'm doing. Okay, so there is some notion of sort of temporal dependency. I can compute syntactically on the PAM. This is some of delta that take two arguments to program and a variable, and that tells what will be the offset. Okay, and I can compute them, and I have some condition that guarantee that my program are causal with my past. So in the past they are 0. There is they can be computed in a causal way, and actually they can compute it compiled into state synchronous transducer, which are known as soon as you cross the ocean as a millimachine. Okay, thank you for your attention. That's almost all. Yes. Yes, so the question is that a real algebra? Are there nice equations that would characterize the semantic of those operators? And yeah, but in any case, yeah, true. Yeah. So first, it really depends on the operator you will use for the fusion, of course. If you use sum, then you may inherit of some mirroring structure, some sum and product. So there are some basic rule making some link with the reset of some signal combined with the signal itself that are inherited from inverse semigroup theory. And otherwise, the other equation I think are just the kind of equation you may find in any functional language programming, depending on the operator you are using. Yeah. Other question? Okay, cool. Thank you.